All right, welcome to chapter 4. This is where I say the fun begins. So we are going to take a lot of the knowledge that you learned in previous chapters and kind of start building on it. And the first topic that we're going to talk about is polynomial and rational functions. This chapter is mainly made up of polynomial functions. You'll have one lesson on rational functions, and then we'll tie the two together with polynomial and rational inequalities. So the first thing we're going to start with is what makes something a polynomial function. So a polynomial is multiple terms with degrees that are whole numbers. And when you're looking at graphs of a polynomial function, they'll be continuous, so no holes or breaks. You can draw them without lifting your pencil. They'll be nice and smooth. There'll be no sharp corners. And the domain will be negative infinity to infinity because there's nothing that you can't square or cube or do to an exponent 5. So here's 4 examples of polynomial functions. Here's 4 examples that aren't polynomial functions. When you look at these, right, there's just nice exponents. They're all whole numbers. There's integer coefficients. Whereas when you look at this one here, you've got an absolute value function. This one you've got a radical function because the exponent is rational instead of an integer. Or instead of a whole number, I should say. This one's another radical function, and then this one's going to be a rational function because there's an x in the denominator, and then you can see that you couldn't draw this without lifting your pencil. Whereas these ones, you're like, oh, such a nice smooth curve. Okay. So let's delve into these polynomial functions in more depth. So one of the first things you need to know is what type of polynomial function that you are going to be graphing. And one of the ways of determining that is to look at what we call the leading term. The leading term is the term with the highest power of x. So for example, if you look at an equation like y, or f of x, is equal to b, that would be something like y is equal to 3. There is no x because the exponent on x would be 0, which is why this is a degree 0, and this would be a constant function. This would actually be this graph down here. So this is an example of a constant function because it doesn't change, right? It's a straight line. If the highest exponent on x is a 1, we're looking at a linear function. I can scroll up. If we are looking at the highest exponent being 2, it's a quadratic. If the highest exponent is a 3, it's a cubic. And if the highest exponent is 4, it's a quartic function. So let's just practice pulling out those key things. So the first thing we're going to do is pull off the leading term. So the leading term is the term with the highest exponent on x. So if you look at this polynomial function, it would be your 2x cubed. The leading coefficient is the number in front of the x cubed, so the leading coefficient is 2. And really what matters about this 2 is whether it's positive or negative. So since there's no negative sign, we know that this is a positive leading coefficient. The other thing we want to look at is the degree. So this one's a degree of 3. But again, just like the leading coefficient, I actually don't care that is 3 specifically. I care that this degree is odd. But the 3 is going to allow me to classify this polynomial function as cubic. All right, why don't you pause the video and try this one. So for this one, they tried to trick you by putting them not in descending orders of power. So for this one, this is your leading term. So it's negative 3x to the 4. The leading coefficient is negative 3, which is a negative number. The degree is a 4, which is an even degree. And because it's a 4, we will call it a quadratic function. All right, then what about this one? So this one is written as a product of linear factors instead of a list of terms. What we want to look at is what would happen if I multiplied this out. Now I know that if I multiply a binomial times a binomial, I end up with a trinomial where the highest exponent is a 2. So if I multiplied this out, I would end up with an x squared. Now I would technically get x squared. Sorry, just want to make my bracket bigger. X squared minus 4x plus 4. I can't write 4s. There we go. Times x plus 1. And if I expanded that out, I would have x squared times x, which is going to end up with an x cubed as the highest exponent. when I multiply them through, like the rest of them, nothing would go as high as the x squared times the x. So I know that this is going to have a leading term of x cubed. And then the coefficient on that, because when I multiply x's together, I just get x, but then I would multiply the 3 through in the end, so that my leading term would be 3x cubed. So the number out front of the brackets ends up being your leading coefficient, and again, we just care that this is positive. And then the exponent is a 3, which is an odd number, and because it's a 3, this would again be a cubic function. Okay, so we're going to have some language around polynomials. We're going to be able to say whether they're cubic or quartic or quadratic and so on, and we're going to be able to identify their leading terms. Why do we care? Well, once you know the leading term, you can do what we call a leading term test. The leading term test determines the end behavior of your graph. So it'll determine the beginning and the end of the graph, but not the middle. So what I like to do is show you a demonstration of this using Desmos. So what I'm going to do is look at different leading terms, so different degrees, and see if there's any commonalities. So for example, if I start with odd degrees, so there's a reason we only cared if they were odd and even. I'm going to graph something like y equals x. Then I'm going to graph y equals x cubed. Then I'm going to graph y equals x to the 5, y equals x to the 7. And I think that'll be enough to prove what we want to get across. Is there anything that you notice about these 4 graphs and their end behavior? In other words, where they start and where they end, right? So the ends of the graphs, where would they be? Well, if you look at them, every single one of these graphs starts down here in quadrant 3. Like if I were to zoom out, they're all in this quadrant 3, and they all end in quadrant 1. So this is the thing we're talking about, is that the degree of your polynomial, whether it's odd or even, can determine which quadrant you start in and which quadrant you end in, so the end behavior. So these are all odd degrees with positive coefficients. And I could go and make these super complicated, like I've just done x to the 7. But let's make this x to the 7 minus 3x to the 3 plus 2x squared minus 4. Okay, so I've made this equation more complicated, so I've added more terms to it. But it's still an odd positive graph determined by its leading term. And the end behavior is that it still starts in quadrant 3 and it ends in quadrant 1. So every single graph that is an odd exponent with a positive coefficient starts in quadrant 3 and ends in quadrant 1. Now, can you guess what's going to happen when I make these odd with a negative leading coefficient? So instead of having y equals x, I'm going to put y equals negative x. Now, if you remember from chapter 2, a negative out front, not in a bracket with the x, is going to give you a reflection of the y values over the x-axis, which means that all of these graphs are going to flop. So if I reflect all of these in the y values over the x-axis, now their end behavior is that they start in quadrant 2 and they end in quadrant 4. So if we go back to our note, right, when we look at our odd degrees, our odd degree with a positive coefficient starts down here in quadrant 3 and ends up here in quadrant 1. All of our odd degrees with negative coefficients start up here in quadrant 2 and end down here in quadrant 4. Now, you by no means need to memorize this. I'm going to show you on your formula sheet where to find this information. So I've pulled up our formula sheet, and I want you to look at these 2 graphs as your odd functions, right? So this one has the highest exponent of 1, it's a linear function. This one has the highest exponent of 3, so it's a cubic function. But both of these are odd positive graphs. And you'll notice that both of them start in quadrant 3 and end in quadrant 1. So every odd positive graph looks like this, whereas if you had an odd negative, you could picture these graphs as reflections. That one wasn't very well. As reflections over the y-axis, and they're starting in quadrant 2 and ending in quadrant 4. So I find some people on their formula sheet, there is nowhere for chapter 4, so I left all this space at the end. So my thought was that if anybody wanted to write down formulas or any information for chapter 4, they could kind of write it down here. So if you wanted to say end behavior for an odd positive graph, you could put something like 3 to 1, and you could make yourself a little chart or whatever it is. Or if you're a purist and you don't want to write on your formula sheet, which I totally understand because most of you are going on to higher levels, learn how to use these resources. Be like, oh, right, this is an example of an odd positive graph. Where does it start? Where does it end? Okay, so we've covered the odd degrees. Now let's go to the even degrees. So if I were to change all of these degrees to even exponents, we want to look at what they would look like. Let's start with the even positive. Now, having just talked about the formula sheet, when we're talking about an even positive graph, I want you to think about what's your base function that is an even exponent that's positive. Hopefully you're picturing a parabola. Can you picture where that parabola starts and ends? Well, let's look at 4 examples of different even positive graphs. So we'll start with x to the 2, x to the 4, x to the 6, x to the 8. This is 4 examples of positive leading coefficients with an even exponent, and every single one of them has an end behavior of starting in quadrant 2 and ending in quadrant 1. On your formula sheet, right, you're picturing your quadratic function. It's starting in quadrant 2, it's ending in quadrant 1. If we were then to make the leading coefficient negative, you'd have a reflection of the y values over the x-axis, and now what would my end behavior be? Right? It would start in quadrant 3 and end in quadrant 4. Start in quadrant 3, end in quadrant 4. Start in quadrant 3, end in quadrant 4. Start in quadrant 3, end in quadrant 4. So that we could summarize that every even graph with a positive leading coefficient, I'm trying to not forget what I'm talking about, is going to start in quadrant 2 and end in quadrant 1. Where every even degree with a negative coefficient is going to start in quadrant 3 and end in quadrant 4. And this is going to help us a lot with graphing. It's going to say, okay, where should I start my graph and where should my graph end? We could also look at a collection of graphs and determine which equation they would match to just solely based on their end behavior. So for example, if I look at this first polynomial function, this is an even degree with a positive leading coefficient. So it's an even degree with a positive leading coefficient, which means that it should start in quadrant 2 and end in quadrant 1. I'm thinking of y equals x squared. And the only graph that does that is D. So this number 1 function would correspond to graph D. All right, pause the video, try these next 3, or keep watching and then pause when you're ready. So if I look at this one, this is my leading term. It has an odd degree with a positive leading coefficient, which means it's going to start in quadrant 3 and end in quadrant 1, just like a y equals x graph or a y equals x cubed graph. So the only graph that matches to that is A. This next one, here's my leading term. It has an odd exponent and it has a negative leading coefficient, which means it's the reflection of the 3 to 1, which means it's going to go from 2 to 4. So if I find the only graph that starts in quadrant 2 and ends in quadrant 4, it's B. Now I know the remaining one is going to be C, obviously, but let's just prove it to ourselves. So again, this is my leading term. It has an even degree with a negative leading coefficient, which means it's the reflection of my first graph, which was the 2 to 1, so the parabola opening down. So it's going to start in quadrant 3 and end in quadrant 4. And again, the only graph that does that is C. All right, so that's the first lesson of this section. Go and try the questions in the textbook.